What's going on, you guys? So today we're going to take a look at maximum depth of a binary tree. So there's a simple solution to this one that is a little bit less efficient than a little bit more difficult solution. So we'll start with the simple solution, analyze space and time complexity, and then we'll go over the difficult solution and do space and time complexity for that one too. Okay, so what are we given here? We're given this tree, and we need to figure out what is the max depth. So we see it's 3, so how are we going to figure out what the max depth is? So we can think about, we can notice here that if we have a root node, if we know that the tree at least has 3, we know the depth is at least 1, and then it will equal so the depth of the tree is going to be 1 plus the max depth of both of its leaves, right? So the max of 9 and 20 plus 1 will be the depth of our tree. So in this case, the max depth of 9 is just 1. The max depth of 20 is 2. And so the depth of this tree is going to be 1 plus the depth of 20, which equals 3. So recursive solution, 1 plus max depth of root left, and we're taking the max of this, So 1 plus the max depth of the leaves will give the depth of the tree. And we also need a base case. So for example, so we see here that left and right are set to null. So for example, 9 will have 2 leaves, but they're set to null. So if we get null, we want to return, if root is null, we want to return 0. So that's it. That's the simple solution. And let's think about space and time complexity. So time complexity, you're going to have to you'll have to touch every single node in the tree. So it's going to be O of n time complexity. And, okay, let's see. And then let's think about space complexity. So we're going to recursively call max depth on each of the nodes. So it's going to be O of n space complexity. Right, so there's going to be a call stack, and the computer is going to first put max depth of 3, and then it's going to put max depth of 9, and then it's going to put max depth of 20, and max depth of null, and 15, and 7. So the call stack is going to fill up. It's going to take up space. So that's why this solution isn't super efficient. Let's just make sure that this is working. So if root is null, give us 0. Otherwise, give us 1 plus the max of the leaves. And we need to import that max function. Okay. So let's think about doing this iteratively. So this is a simple solution. So if you're in an interview, the interviewer is probably going to ask you for the iterative solution because it's a little bit tougher. So let's think about doing this iteratively. So we could traverse traverse the tree in either a depth first search or a breadth first search. And so either of those ways, so there's a couple ways that we could do it. I think we'll do depth first search here. And so the idea will be that, let's think about this. We'll create a stack, and we'll create a depth stack. We'll create 2 stacks. We'll create like 2 visit nodes to visit. I'll just call them nodes. Nodes and depths, 2 stacks. We'll add the root, and we'll do our check. If root is null, return 0. And we'll add our depth. So if we have a root node, it has at least depth 1. And then we'll visit different nodes in a depth first manner. So let's think about this. Okay, so we'll have a variable depth, which will end up returning. And so let's see. So while nodes is not empty, what are we going to do? We're going to say, we're going to visit the next node. So we're going to say current node is stack dot pop. So pull off the most recent one placed on there. Current is stack dot pop, and current depth is depths dot pop. Okay, and let's see. So when we get to 9, we're gonna push null onto the stack. But if we have null, we want to just move on to the next one. So if current does not equal null, so we'll skip this if it is null. Oh, we don't need this for our pseudocode. Okay, what are we gonna do? We're gonna say depth is equal to the max of current depth and depth. Okay, and then we need to add the neighbors to visit. So we're going to say nodes dot add current dot right, and depth dot add current depth plus 1, right? Because this is going to be a child node that we've popped off the stack. And we need to add the left side too. And it'll have the same depth. And so we add right first, because that way we're going to add right, left, and then when we pop, left will come off first. Is that right? Yeah, so we want to, yeah, so depth first search, it goes down the left-hand side first. Or it could go down the right-hand side. But in this case, we're going to do the left-hand side. Okay. And the difference breadth first search, it would look at all nodes on one level before moving to the next level. In a depth first search, it jumps levels. Okay. And then what? So once the stack is empty, we've set depth to the max depth we've encountered, and so we just want to return depth. So let's give that a shot. So we'll keep our null check. We'll create, and so for nodes, for a stack, we're just going to use a linked list. Import java.util.linkedList. Okay. So we're going to get a var nodes, and this is going to equal a linked list of nullable tree nodes, because we could have null in there. Okay, and then we're going to create depth, and this is going to be ints. Int. We're going to nodes.add root and depth.add 1. We're going to create a var depth. We could just, let's call it max depth. Makes it clear what it is. Okay, so while nodes is not empty, so is not empty, we want to I could copy this. I'll just write it out. Okay, so var current is nodes dot poll last, and that's how you pop the last element off a linked list with poll last, and current depth is depth poll last. And then we're gonna do our check for non-null values. And once we're in there, we're gonna set a new max depth equal to the max of current max depth or max depth and current depth. Okay. We're going to add the right, current.right. We're going to add the current depth. And then we will return depth, max depth. Is that right? Let's make sure we did that right. We'll find out. Okay. Tree nodes. Tree node. Okay, there you go, guys. So time space complexity for this one, let's think about that. So same as the recursive solution, we're going to have to visit all of the nodes. So it's going to be O of n runtime. And then space complexity, we just have the one call to max depth. Whereas the recursive solution had n calls. And then let's think about what space are we using? We're using space for we have the linked list that we need to keep in memory, the two linked lists. And those are worst case size n. And so here's my question for you all. So we're getting basically the same memory usage, 35 and 35 for the recursive and the iterative. Does that mean that they're using the same length? Like if n was quite large, would they still be the same or would they be different? The call stack for this guy, for the iterative solution, is 1. We only call max depth once. But the linked list size can be O of n in a worst case. So is the fact that one variable could like take up all the elements, does that mean that the space complexity is O of n, or is it O of 1? So I'm not sure here. Is this O of n or O of 1? If you guys know, let me know in the comments. Or O of n. We are not sure about space complexity for this one. All right, you guys. That has been maximum depth of a tree. What do they call it? Maximum depth of a binary tree. All right, guys. See you next time.